Hello, everyone. Thank you very much for being here. My name is Fanyin Zheng. I'm an assistant professor at Columbia Business School. I'm very happy to be here to tell you about our paper on improving match rates in dating markets using display optimization. This is a joint work with Ignacio Rios at UT Dallas and Daniela Saban at Stanford. Our paper is motivated by the online dating industry. So it's been a very important industry in recent years. I'm guessing some of you in the audience might even have firsthand experience. It's generating a lot of revenue. And our work is in collaboration with one of the major dating platform in the US in thinking about how to improve match rates. So our platform works as the following. So a user, Winky, signs up. When she signs up, she's going to report some characteristics about herself and preferences over others that she's interested in being matched to. And after she signs up, when she logs in every day, she's going to be presented with a set of users, profiles that the platform selects. And then she's going to evaluate these profiles. So she likes Squinty, for example, and she doesn't like the other two. And similarly, Squinty is going to evaluate the assortment that she evaluates. She was presented. And then if at some point Squinty was also presented Winky and also liked Winky, then a match is formed. So each user sees an assortment of profiles and likes and dislikes them. And if they a pair of users like each other, then a match is formed. Then the question we're interested in is how do dating apps decide which profiles to show? So we do 4 things in this paper. So first, we're going to propose a dynamic model of dating app where we're going to allow users to repeatedly interact with the platform and also allow for detailed agent-specific or user-specific utilities. And then using data that comes from our partner platform and using some quasi-experiment, we're going to try to understand user behavior and estimate their utility functions. So here we propose a novel identification strategy of to estimate a dynamic effect. And then we're going to use our estimation results and our model to propose an algorithm for the platform to select assortments for each user in each day. So here we're going to account for the impact of users' past experience with a platform on their future actions. And we want to account for that in a simple way. And finally, we're going to implement this algorithm through a field experiment. And we show that 27% our algorithm achieves 27% increase in total number of matches compared to the default algorithm used by our platform. So we think of this as end-to-end market design, and we think that our work hopefully would inspire interesting theoretical, empirical, and behavioral questions. So how does our model look like? So let me tell you a little bit more about the problem. So Winky first reports a bunch of characteristics and preferences when she signs up, as I said before. And using these information, the platform is going to find a set of potential partners for Winky. And then there are these backlog users, backlog profiles, which are going to be users who liked Winky in the past and Winky has not seen yet. Okay, so because Winky is a new user, maybe her backlog is empty, but Squinty here might have been interacting with the platform for a while, so Angry is in her backlog. And then using the information from the potential partners and the backlogs, the platform is going to select the assortments, so the set of profiles to show to each user on each day. And then the user evaluates these profiles. So Winky likes Squinty, for example. And then the set of potential partners and backlogs are updated on the next day. So the potential partners of Winky are going to be updated. So the assortments that are shown on day one for Winky are going to be removed from the potential partners because she already saw them. And then the backlogs are also going to be updated. So because Winky liked Squinty on day one, so Winky is going to show up on as a backlog for Squinty on day two. Okay, and then again, the platform uses these updated potential partners and backlogs to select the assortment for the users on day two. And if at some point, a pair of users like each other, a match is formed. And one important thing here is, as an example, illustrate the match does not need to be formed within one period. They could be formed asynchronously, and most of them do form asynchronously. And also, users do not leave after their match. So users repeatedly interact with the platform. Okay, so the decisions for the platform is to select the daily assortment for each user. And the objective here is to maximize the number of matches. Of course, there are some constraints that need to be satisfied. In the interest of time, I won't go into details. And the complication here is the dynamics. Okay, so users interact repeatedly with the platform. There are constraints that need to be satisfied every period. And also new information is available after each day that need to be taken into account. Okay, so our model is going to look like the following. So we have inputs, which are sets of users with characteristics and preferences. There's going to be a fixed horizon and assortment size. And this is a dynamic problem. So as I said before, we select assortment for each user in each period. User logs in, evaluates the profiles, and then the platform is going to update potential partners and backlogs and notify also matches. And then the process repeats on the next day. So the objective here is to design a dynamic algorithm to maximize the expected number of matches. Couple of observations. One, the problem is computationally hard. And second, we need to understand from the data users like and dislike decisions, which is what we're going to do next. So the data we have is user characteristics and assortments selected, the user logins, user evaluations on each day, and the full access to our partner's default algorithm. So how are we going to go about understanding the like and dislike decisions? So we're going to model the like decisions based on the utility function. So UIJT is bigger than some outside option UI0. If I is going to like, user I is going to like user J in period T. Okay, so one question that we're interested in particular is, does this decision, the like decision, depend on I's recent experience on the platform? So for example, the number of matches in the previous period might affect the like probabilities in the current period. Okay, so if the answer is yes, then it means that users react to the algorithmic choices of the platform. So assortments, decisions today is going to affect the matches today. And then matches today is going to affect users' like probabilities tomorrow. So as a preview, what we find is that the number of matches obtained in the recent past has a large and significant negative effect on like behavior in the current period. Okay, so we want to estimate users' utility function, UIJT, in a linear form. And the main thing that we want to estimate in particular is this gamma coefficient, which is the coefficient on I's matches since last session. The challenge here is that we want to recover gamma here without bias. So we want to make sure that gamma has a causal interpretation. And there's a complicated endogeneity problem because number of matches since last session can be correlated with unobserved preferences of user I, unobserved activities of user I, both on the platform and off the platform. And also, it's not feasible to run a randomized experiment because of deception and also interference due to the two-sidedness nature of our problem. So what we're going to do is we're going to estimate gamma through a quasi-experiment. So I won't go into details here, but we use a change of the platform's algorithm as a quasi-experiment. And this change increases the likelihood of getting a match for treated users, but not for the control users. And we have to make sure that the change is going to be exogenous, uncorrelated with users' preferences and activities. And the change also does not introduce interference, which is important in our setting. We find that an extra match reduces the like probability in the current period by 3.2 to 6.3%, which is significant. Okay, and then using these results, we're going to propose a heuristic, which we call the dating heuristic, as the algorithm to select assortment for our platform. So first, we show that one can construct a linear program, which is an upper bound, if we ignore this dynamic effect. Okay, and then using this linear program, we're going to propose this heuristic with one period look ahead, which has two steps. So first, we're going to decide which profiles to show we introduce a linear penalty term to account for the effect of today's decision on tomorrow's matches. So reintroduce our dynamic effect here. We saw this LP from the upper bound. And then in the second step, we're going to round our solution, okay, to satisfy the business constraints following the priority order of our partner. Okay, so how does the algorithm work that's different from the current practice or the default algorithm? So we use personalized estimates for like probabilities. That's number one. Number two, we explicitly account for the probability that a profile is liked back. Okay, so we're maximizing a number of matches, not just the one direction like. And then we also account for user activity and recent experience through this dynamic effect that were estimated, and also the frequency by which the users log in. So what we show through simulations is that our algorithm improves match rates by 25 to 45%. And then we implement our algorithm through a field experiment. We look at three largest markets in Texas: Austin, Dallas, and Houston. So Houston is randomly picked as the treatment markets, and then Austin, Dallas are the control markets. We run our experiment for 1 week, and what we see is that there's a significant increase in terms of total number of matches in Houston relative to Austin and Dallas. And if we do our diff and diff estimation, we show that the number of matches increased by 27% on average in Houston. Okay, so we also have some evidence that show that the mechanism of our improvement is because precisely that we generated better assortments. Okay, so to conclude, few things that we learned from this paper. We learned that display optimization plays a very important role in semi-decentralized online matching markets, online matching platforms. There's a lot of work on advertisement, assortment, retail assortment, display optimization, but not so much for matching. We showed that modeling the impact of the algorithm has on the user's decision in future periods actually is very important. We have some evidence of that, and we also provide a novel identification strategy to account for this phenomenon. We show that in our setting, this is going to actually accounting for the user's reaction is actually going to lead to a substantial amount of improvement. And we think that there are many interesting theoretical and empirical questions on managing dynamic decentralized matching markets. And that's all. Thank you very much.